All right, welcome to the first lecture in EC Fundamentals 1. I hope you enjoy this journey with me as much as I will enjoy it with you. So in this lecture, we're going to focus on understanding charge and current, which are the two first fundamental quantities we're going to be dealing with. And later on, we're going to start understanding voltage. Before we go directly into what is charge and what's current and how do we calculate them or why are we concerned with them, I wanted to really go back on what matters most. And what really matters most, which will be with us for the remainder of this class, is actually power and energy. And one of the things I would really like you to remember is that every quantity we're going to calculate here is really calculated precisely because we want to understand how much power and how much energy our system consumes or delivers. These are the two fundamental quantities in nature, and you may actually remember from basic physics that the power that the system consumes or delivers is nothing else but the rate of change of energy. So if you know the energy, which is usually measured in joules, and you know the rate of change, the time is usually measured in seconds, then you can basically calculate the amount of power usually measured in watts. But normally in electrical circuits or electronic circuits that we're going to be discussing in this class, the way to find this power is by knowing the voltage, which we have not defined yet, and the current, which we will define in a minute. So that's why we're going to be using those quantities, because finally we want to find power and energy. So let's talk about current first. And I would really like you to take a quick look into what happens inside the conductor. So if you can just picture for right now a piece of copper or a piece of aluminum that you can find in most conductors today, in most circuits with conductors today, if you were able to take a magnifying lens, you would find that inside you have some free electrons. And what I mean by free electrons, I mean electrons that have the ability to move. So if you're looking at this conductor at some type of a temperature, T, then you will find that those electrons are in some type of a random motion. They will be going in all kind of different directions, and the net result of that is basically a totally zero net flow of electrons. That's exactly what happens in real life if you just take a piece of wire and you just place it on the table. However, if you go and take now exactly the same conductor, but you actually connect a source to it, the most common source you can imagine is basically just a battery, then you will find out that now those electrons are feeling a force. That force is directly proportional to the electric field that will be established inside the conductor, and that means the higher the electric field, the higher the force. Now, those electrons are definitely not sitting inside the conductor all by themselves. They actually have some ions, and those ions, under normal conditions, are basically stationary. So those electrons will find themselves colliding with those ions, and in a classical sense, they will also find themselves colliding with other electrons. But eventually, after all of these collisions are taken into account, there's going to be some average speed with which they're going to move, in this case, to the left. And it's precisely this average net speed that those electrons will have that we can see as flow of electrons, or as we call it in physics, as current. So in other words, if you were to count how many electrons per second are basically moving to the left through the cross-section of this conductor, you will be able to find out exactly the amount of current that you will have. So in a slightly more precise sense, the amount of current that we have, which here I use the symbol I, is nothing else but the rate of change of charge Q that moves through a cross-section in time. If you have electrons, all you have to do is multiply the number of electrons n with the electron charge to find out the total amount of charge that you have moving through that cross-section. So once again, the current, which is measured in amps, is nothing else but the rate of change of charge, coulombs, per second that you have flowing through a cross-section. Of course, with this type of definition, you can essentially also find the charge. So let's say you can find the total charge that moves between two times, let's say between time t0 and t, if you know the current. So all you have to do is basically integrate the current, and then if you integrate it from time t0 to time t, you can find basically the total amount of charge. If you are a little bit confused about using the integration variable t, as well as using the same t on the upper side of the integral, you can write this as simply t0 t, then I of x dx. Now, you may actually notice something a little bit strange in this figure. What is strange in this figure is that the speed or the net direction of the electrons is to my left, while the current I here is pointing to the right. And that is because of historical reasons. So in the very beginning, when all of these concepts were being developed, people actually thought that it was the positive charges inside the conductor that were moving and not the negative ones. But it turns out that it doesn't matter if you consider a positive charge to move to the right or a negative charge to move to the left. The result is one and the same. And so that basically has led us to accept the conventional definition of current as being the opposite of the flow of electrons. So in real life, negative charges, electrons move in most cases. However, the current direction you will see in circuits, because of historical reasons, it will be to the opposite of the electron flow. Now, the other thing you will find out, and we have to be careful here, is that it is not enough to simply calculate the I as dq dt, the rate of change of the rate of flow of charge, but it is also very important to correctly signify the direction of the current. So if somebody tells you, I have 1 amp of current flowing, it is not sufficient information. You have to be able to say which direction the current is flowing. And of course, current flowing of 1 amp to the right is the same thing as negative 1 amp flowing to the left. But I just really want you to understand that finding a direction of the current is as important as finding its actual value. I also would like to emphasize that finding direction of current and finding the actual value is not just done in the schematics you will be seeing over and over again in this class, but it's something that we deal with in many, many everyday circumstances. So here is an example you can, I'm sure you can be familiar with. You may have already experienced that. So this schematic here is basically showing a power strip where essentially you have connected a bunch of different devices. For example, you might have connected a computer that may be drawing 5 amps of current to work. The TV may be on at the same time. You're multitasking a little bit, while at the same time you're basically playing a game in your game console. In a typical house scenario, this power strip is not directly connected to the grid to give you the power you need, but is rather connected through a breaker box. What's the breaker box? A breaker box is a little bit like insurance, in the sense that there is essentially a breaker here, a circuit breaker, a current breaker, which is going to stop the flow of current, essentially stopping the flow of power, if you try to draw too much current. And there could be several scenarios where you might actually draw too much current. For example, you may have an accident or you may have a short circuit. So if there is some type of a bad connection that would attempt to draw more current than the circuit breaker indicates, in this case the circuit breaker is 15 amps, then the circuit breaker will trip and will essentially create an open circuit stopping the direction of current. If you do a quick calculation here, so 5 amps plus 6 amps plus 3 amps will basically give you 14 amps of current flow. This is barely below the 15 amp limit, and therefore all 3 of these devices can actually work together. But if you try to connect one more device, let's say a hair dryer after you took a shower, that would require another 2 amps of current, then this will immediately trip the circuit breaker, because now you have basically exceeded the maximum and you have reached to 16 amps. Here I have also made the assumption that all of these currents are adding up together, and as we're going to learn later on, this is a fundamental law called Kirchhoff's currents law. Now, in everyday situations like the one I'm describing right here, we can understand much more easily what's happening if we draw a circuit diagram. And so as you can see here, this is a very simple circuit diagram that has the source that we're connecting our devices to. This is the 120 volt AC source. Later on, we're going to discuss those in much more detail. We have our circuit breaker that will trip if we try to bring more than 15 amps of current. And then we have one by one all the devices that we have connected to this network, each one of them drawing the amount of current that requires when it's on. So what is going to be interesting in this class is that a lot of times we'll be starting from here. We'll be starting from a diagram that essentially typically simplifies an everyday situation. Just because I won't be showing you all the time what the real life scenario though is, you should not get the understanding that we're talking about theoretical circuits. Every single diagram that we'll be discussing in this class, or nearly every single diagram that we'll be discussing in this class, is actually a simplified scenario of a real life circuit. So thank you for being with me for this first lecture, and we'll see you next time.